Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure and honor to welcome CONSANI, who will report on her very recent work with Anaon, because I just saw your paper in the archive and the abstract was basically very similar. So I bet it's exactly this. So we are very happy to have you here. So it's primes, knots, and the scaling site. But please be gentle on us because many of the things we are talking about are well, difficult for us. So please be as generous with your explanations as you possibly can. It will be much appreciated. Thank you so much. The Zoom is yours. The floor is yours. Take it away.
Thank you, Piotr. And thank you all the organizer for inviting me to give the talk at this seminar, still running seminar online. Yeah, so in this talk, I will present, as Piotr said, I will present some very recent results, which is part of the collaboration project I have with Alain Cohn since several years. And yes, this has to do with, the topic is contained, the development I'm talking about today is written in a preprint, which appear on the archive in January. So this, the subject of today's talk is about primes, in fact, rational primes, understood or thought of as knots in a three-dimensional sphere. So this is the typical topic of arithmetic topology, but the talk will present, obviously, the non-commutative geometry point of view on these ideas, on these kind of already old ideas. Okay, so let's see if we can use. Okay, so let's introduce a little bit the étale topology, étale cohomology. So the story started, if I'm correct, because I was not there, in the late 50s when Grothendieck introduced the main subjects of Galois theory of schemes. In particular, the idea that a point of a scheme, what nowadays called a geometric point, has automorphism. And so this was not present in the Zarinsky topology, in the classical, so to say, theory of schemes. The whole idea, in fact, produced SGA1, and together with some very essential idea from Jean-Pierre Serre, is still very well known, his talk at the Séminaire Chevalet in 1958. So with the introduction of certain ideas of his, then finally Grothendieck was able to introduce the correct refinement, say, of the Zarinsky topology for a scheme, which also includes this viewpoint of Galois theory for schemes. The development, in fact, was rather lengthy, if I'm understanding correct, and because they needed some auxiliary technical results from commutative algebra, in particular in the topic of Euclidean rings that Nagata developed earlier on in the, say, middle 50s. And eventually, in collaboration with Mike Artin, Grothendieck defined the étale cohomology. Well, in the same time, I'm told and I read that David Mumford started to think about, as a consequence of this project of étale theory, étale cohomology running, start to have some ideas on the interpretation of primes in number fields, in the ring of integers number field, and in particular for the integers, as kind of knots in this three-dimensional sphere. And in the late 60s, early 70s, Barry Mazur came up with the first computations of what you have seen, you can see here as the cohomology of the spec Z with coefficients in the sheaf GM, in the group, in the sheaf of groups GM. The choice of GM is not casual because GM is an abelian, is a sheaf of abelian groups. It contains the full package of sheaf of roots of unit using which the étale topology provide the most interesting results. So torsion sheaves in étale topology for schemes. So here you see the spec Z.
Question. Excuse me. May I have a stupid question? So why I equal to 3 is exceptional?
Free exceptional what?
In this formula, there is exceptional formula for I equal to 3. So what is the intuitive reason for this?
Yes. So you want to see an intuition of these results, you mean?
The last one.
The last one, Q mod Z for I equal 3. Yes, I will develop a little bit on why we get this result. Yeah.
Okay.
So you see here, exactly, you see here a behavior that we, for a suspect Z, that we wouldn't have seen if we were working in Zarinsky. For example, the fact that for I equal 3, when the dimension of the scheme is supposed to be 1, topological dimension, here we have some non-zero contribution. And the story, well, it's story, to get to this result, it's a kind of lengthy proof which involves a short exact sequence of sheaves of this type, and in particular, the fact that we play with the generic point of spec Z. So we play with the generic point, we introduce the map of the generic point in spec Z, and out of it, we construct these short exact sequences of sheaves of étale in the étale topology. So here you see that from the exactness and running with when you have a short exact sequences of sheaf, and if the cohomology is well managed, is well determines, you have a long exact sequence of cohomologies, and then one start to run in the long exact sequence of cohomology. For example, interpret the H0 here as Z mod 2Z because the global units are plus or minus 1. You take the H0 of GM for Q, and then you have a Q cross. Then you take the H0 of this part, and you have the full collection of integers, so a direct sum running for all primes in spec Z of Z, and then you move to H1 of GM, and you take, and therefore you conclude by the étale theory that is still what we expect to be in Zarinsky, the Picard group, which in fact vanishes in this case because Z is UFD. And then you move to H1 of GM and H1 of this part, which are both 0. And then you move to H2 of GM, of spec Z with coefficients in GM, which is written here. And the vanishing at this point requires further knowledge on number theory, global class field theory in the way I've written here. So there is a short exact sequence of Brouwer groups. Brouwer groups are the cohomology, the second cohomology in this particular setup are described as the role of the H2, say S, S, G star, this image. So this is the Brouwer group for Q. Then you look for the H2 of this sheaf, and then you get the Brouwer group of the local field contribution, and so on. So there are certainly some results behind which needed to be known from number theory, as I said, from global class field theory, global and local class field theory, which allow, first of all, to conclude that there is an inclusion of H2 in the Brouwer group of R. This is, I mean, kind of really new in the sense that you don't expect a priori, because the prime in spec Z are not Archimedean, the non-Archimedean one, but nonetheless, because there is this sheaf involved where there is Q with all its places, non-Archimedean and Archimedean, that you start to see the Brouwer group, for example, of Q and the Brouwer group of the local field of the Archimedean component, which is the Brouwer group of the real. Even though the spec Z, as I said, doesn't involve the prime at infinity. So this sequence can be shown to be exact, embed the Brouwer group of the real, which is this it's Z mod 2Z, it's in fact a cyclic group of order 2, embeds in the Q mod Z, and at the end you have the output that in fact there is an isomorphism between H3 SGM and Q mod Z. So this is the reason why you get something in I equal 3 index, which is a priori, I mean, naively say, a priori unexpected. So behind the scene, the contribution of the whole collection of primes, Archimedean and non-Archimedean, in this case, implies the fact that the H3 is isomorphic to Q mod Z. If you go higher with the index, higher than 3, then there are many vanishing. For example, there is a vanishing, here is some tech results, a vanishing of the HI of Q and the isomorphism with the HI of R for this sheaf, which is GM, when I is at least 3 and odd. In the even case, remains the fact that the Brouwer group, the cohomology of R with coefficient in GM is periodic. It's periodic and has order 2. So it's still there for every integer greater or equal than 4 even. And the many vanishings in terms of the cohomology of the local field, the finite field, the cohomology of the finite field, implies that in fact the cohomology of spec Z when I is at least 4 as the description which I gave here. So in case someone wonder, but I don't know, maybe someone wonder, what about if I had then taken the Arakelov compactification of spec Z and include therefore in spec Z the Archimedean prime? What are the consequences of this? What would be the cohomology? So then in that case, because the Archimedean prime is included, you don't have this, the fact that you still have HI in I degrees, I greater or equal than 4 even, to be Z mod 2Z, and the cohomology will vanish after degree 3, so from degree 4 on. But that's just for, okay. So here is so this is a result. In fact, this is the result that essentially was proven by Mazur in the late 60s, early 70s. In fact, in a more general context of the spectrum, the algebraic spectrum of the ring of integers of a number field, you might wonder, what about if there are, if rather than Q, you take a number field in which there are the Archimedean primes, so to say, the Archimedean valuation, some are complex rather than real. Well, they don't really get any contribution in this cohomology. The only one that get contribution are the Archimedean real primes. So in terms of knots, in terms of the connection between prime and knots, then it's like thinking of spec of FP, a point, but understood as a knot because in a tal cohomology, in the pi 1, in a tal cohomology, Abelianized, but in this case, even without that thing added, this comment added, is the Galois group of the separable closure of FP over FP, which we know to be Z hat and generated by the Frobenius. So, okay. So the analogies with knots at this point is that because a knot, in fact, when embedded in S3, has a behavior homotopically speaking, which is this. So the knot is a type of Eilenberg-MacLane space where the homotopy, essentially, homotopy is the abelianized homotopy group. It's only in degree 1, which is Z. So for the prime, people thought that there was some analogy with the case of the prime understood as this little knot, Kp, because homotopically speaking, and the modulo 2 torsion, which is revealed here, this Kp, this homotopy, this abelianized étale homotopy groups of the spec Fp, they are in fact only essentially in degree 1. So, this is the result. There is more, in fact, in this analogy. So S3, the three-dimensional sphere, is too connected. And here we see the counterpart in degree I equal 2 for the spectrum of Z. There is a three-dimensional Poincare duality, which holds for obviously for the cohomology of the sphere, and the H3 is Z. Rather, here we have a version that is more number theoretic flavor, so to say, because all primes contributes with a sort of torsion. And there is a fact now in number theory. In number theory, people know that if you take the algebraic closure of Q, this algebraic closure can be reached by stepwise, so to say, by finite extension when you include systematically a finite number of places of the field Q at which this extension, and only there, is ramified. So this is the notion which I shortly wrote as S-ramified, finite extension of Q. These extensions of Q are finite and ramified only at S, and S is a finite set of places of the field. So one could think of following this idea, this result, one could think that if one wants to compute the étale cohomology of the complement of a finite set of places in S, what does it mean, pi1 étale? Essentially, it means it computes, it looks at covering, connected, unramified covering of spec Z minus S. So over this spec Z minus S, this covering must be unramified étale. So then they should be described by the definition, by the results I mentioned before, in terms of the Galois group of these extensions, which are exactly ramified at the places S, at the finite places S. So for example, the étale cohomology of spec Z is well known to be trivial, and the reason is the Minkowski theorem, which says that Q, any extension of Q, ramifies somewhere. So it's impossible to search for connected covering of the spectrum of the integers, which are étale everywhere. And therefore, this coincide, is an agreement with the fact that the pi1 of S3 is also trivial. If one starts to take off, and here is the topology, if one take off from S3 and not, and take the abelianized homotopy group, then one discovered that this is Z, and this is essentially Alexander duality in topology. Here is the counterpart in number theory when you take out of Z, spec Z, a prime, which corresponds in quote to a knot, and take the abelianized étale homotopy group, and then results from global class field theory, in fact, tell us that this is in fact, this is the Kronecker-Weber theorem in global class field theory, tell us that this is isomorphic to the Galois group of the extension of Q, which is ramified exactly at P. So it is an abelian and in particular extension which is made by roots of unit which are of P order, P power roots of unit. So it's cyclotomic and abelian and so on. So this is the results from number theory says that this Galois group is isomorphic to the unit of the local ring ZP, the ring of integers of QP. And so for this reason, you see a Z here, you see a ZP star here, and people believe that there is a sufficient analogy to push this idea further. But the point is that so far, the intuition that behind P there is a circle, there is a knot somewhere, and how to look at this knot, how to understand where the knot here, where the circle is just in terms of an abstract results, which is what I underline. So in topology, you've given two knots in S3, two different knots, and people introduce the notion of the link. The link is a number, the linking of the two knots. And in the definition is that you take the image of the generator of pi1k, which is Z, the abelianized one, in the pi1 of the complement of the other knot, the second knot, in the abelianized group. And this is known to be isomorphic to Z. So this is a number, is an integer. But notice what you do in this process. You have two knots which are different, and you map the pi1 of one in the complement of in S3 of the other knots. So in terms of groups geometry, it's like considering the monodromy, which is obtained by lifting the first knot in the maximal abelian cover of the knot complement of L in S3. So this is what one might retain of this machine producing these integers, which are the linking of two knots. So here is the non-commutative geometry interpretation and also an overview of the talk. The idea is...
May I have a question?
We need...
Yeah. May I have a question? So what you said about was this abelianized analogy. Which
the abelianized
depicts closeness of this knot to be simply a circle. But what about the property of being a knot? What about these knotting properties? Can we see them
not involved. This is eventually, but this is not the topic of my talk. The topic of my talk is to, first of all, realize where should we look for this geometric understanding of the knot in number theory, because number theory, as I said, doesn't give you the geometry, doesn't give you the circle, because you have only the prime so far. You have a P, a prime embedded in spec Z, and you see really nothing there except a point. And so the results that this talk is about, first of all, to show you that you don't have only P, but if you introduce the correct non-commutative geometric space, you have also the view of the knot, the view of what is the knot. And second, realize in a non-commutative geometric form the link. So for the rest of these questions, it's still open. Okay, so if there is no comment, I will continue. So what is the space that in fact has more space than the spec of the integers, in which you see not only the prime, but in fact the circle which corresponds to this prime. Okay, so then we have this non-commutative space that Alain Kohn and I introduced several years ago in 2014. which is the scaling site. So the scaling site, it's a quotient of the Adel class space of the rationals that you see here. So it's a quotient when you cut off by z hat star, by the unit of z hat. And we know that this quotient, because this happened for the Adel class space, is acted upon by R star plus. And this space, non-commutative, inherit by its own definition. After all, we work with Adels, the definition involves Adels, inherits the class field theory machine in it, the class field theory machine of Q. So, so now the little prime P that spec Z is able to show to us as a counterpart, obviously, in number theory in terms of a place, in terms of an equivalent class of isomorphism of valuations. And the point of this talk is to show you that, in fact, inside this scaling site, there is a full circle of length log P, which is essentially the orbit of the action of R star plus on P itself, which produce visually, at least, a circle which is attached to P that spec Z couldn't, limited as it is as a space, provide to us. And moreover, now the scaling site has the Adel class space as a covering. And we propose this covering the Adel class space itself as it's the maximal abelian cover of the scaling site, which is obviously acted by the Adel class group. And when one take this orbit CP inside the arithmetic sign and pull it back in the maximal abelian cover, which is the same strategy as in topology you saw in the previous line, do when you want to understand the link of two knots, because you take the first knot and you look at the image of pi1 of the first knot in the complement in S3 of the second knot. Now here you have to remember that S3 would correspond to, in a sense of, at least locally, with this with the maximal abelian cover of XQ. So this pre-image describes, in fact, geometrically the monodromy of the lifting of the prime knots Kp, which is now realized in a more substantial form in terms of this circle. And in fact, later in the talk, you'll see the link. So how this pre-image of CP produce the link to, in fact, any other possible knots attached to a prime Q different from P. This is only the overview of the talk. Now I will enter in each single steps, and in particular, I sort of review the definition of the scaling site so that you can see more visually this definition of CP of this orbit. Okay, so the story starts, as I said, 10 years ago or so, when we were really thinking to attach a topos, a Grothendieck topos, to the non-commutative geometric space, the Adel class space, and in particular the double quotient I spoke about before. So the story started in topos theoretic terms, as introducing with the introduction of the combinatoric site. So you have n cross understood as a small category with a single object, and the elements of n cross now realized as the endomorphism of the single point. And a topology, which is the most, the roughest one, which is the, in Grothendieck words, so the chaotic topology, or sometimes called the indiscrete topology. So the only open are the empty set and the full thing. So if you consider the topos point of view over this site, so take the phantom category, which is made by the collection of pre-sheaf over this site. Actually, pre-sheaf and sheaf is the same thing due to the really rough topology we have at hand. Then they are simply a functor from the dual of n cross as a category to the category of sets. And the arithmetic topos in its simplicity is understood as the Grothendieck topos of a sheaf of sets on this site. So what is an element of this topos is a covariant functor from the dual of n cross to the opposite, sorry, of n cross to sets. And essentially, it's a set. It's a set with an action from the right of n cross. So giving an action from the right on this set is the same as giving, in fact, a collection of endomorphism, one for each element in n in n cross over this set. Or you can be more refined and say, okay, the right action of n cross on the set, this set, which is given to you by the evaluation of f, is determined by a commuting endomorphism of endomorphism of psi p, where rather than n, and then you take prime numbers. So any n decompose as a product of prime, and then you get. So when you have a topos, you have a notion of point. And here the notion of point is like in any top of context that has a point in it. So it's a geometric morphism of toposes between the most basic one, which is the collection, the sheaf of over a point, which is the category of sets, to this topos n at cross. So it's a pair of functors, P lower star, P upper star in its most fancy definition, such that P upper star of any sheaf here is just the evaluation of f at the point. And this pair of functors are, as usual, are one is, so P upper star is left adjoint, they are adjoint functors. So P upper star is left adjoint to P lower star, so automatically is right exact, but even more, in this case, it is exact. So P upper star is an exact functor. So the point itself in P at cross is determined by a filtering functor, and this is an idea of Grothendieck. What essentially you do, you start with the P upper star, which is contravariant. You compose with the contravariant Yonedan embedding that I recall here. And then you have at the end a covariant functor from n cross for the category n cross to sets. And the notion of filtering here means the following, means three important facts. It means that, first of all, the evaluation of this functor at the point is non-empty. And there is a free left action now because there is contravariance involved in terms of family, described by a family of endomorphism, as we saw before. And here is a second important property of beam filtering. So for any two elements in the set that we have at hand, there exists an element, a further element in the set, and two natural numbers, so that you can link x and x prime in terms of this functor applied at k and k primes. And finally, there is a third condition, which is written here. So if, again, x is a point in the set, and if you are given two elements, two natural numbers, satisfying this property so that they produce essentially the same point by means of two different k and k prime, then necessarily k and k prime must be the same. It's a sort of rank one idea. So when in the main results, the main facts that I just collect here that they are described in the paper, the arithmetic site that we published in 2016, I think, are the following. First of all, the understanding of the category of points of this topos, which is canonically equivalent to the category of totally ordered group isomorphic to non-trivial subgroup of Q. So this is the idea. I just quickly review how to do this. So if you start with the point in the topos, then you have the possibility, in view of the action of n cross on the set, which is non-empty, to create the positive part, so a semi-group, which is the positive part of totally ordered group, which I denoted the symmetrization of H being the symmetrization of H plus. And so there is.
Sorry, may I interrupt? It's completely stupid.
Yeah.
Please forgive me. But I'm confused. You write total ordered groups, and when you have age kind of isomorphic to 0, and you write age distinct from 0. You mean?
No, I mean, I meant
that
there is a. Yes, I understand that. Yes.
Right, okay.
Yeah, I meant. Yes, I meant that there was a parenthesis here, isomorphic to non-trivial subgroup. Thank you.
Okay,
So, moreover, yes, the typos. Moreover, any H of this type has a natural inclusion in Q, which is in fact a sort of precise, unique inclusion in Q, which is determined, the fact that is unique is determined by what we have seen before as property 2 and 3. So I do not enter in more details, otherwise I cannot run the full thing. But just to say that there is a one-to-one correspondence between points of these topos and I mean, totally ordered groups that they are in fact isomorphic to rank 1 subgroup of Q, that they are not trivial. The fact that they are not 0, by the way, is due to the fact that we have the first property here. So the second important factor, which brings in the adelic now part of the story so far, is topos and points and groups. So is the fact that if you are given any non-trivial subgroup of Q, this non-trivial subgroup of Q, it's always and uniquely of the form H attached to a finite adele. The finite adele, it's an adele in the finite part of the adeles of Q modulo the units of Z hat star. So intuitively, what's going on? If you start with a subgroup of Q, the subgroup of Q, the elements will have denominator. The denominator will involve primes with some power. And this means that you can build up, in fact, manually the adele, the finite adele, out of this idea. And an adele will be sort of 0, will have P to the N locally at the location where there are, for the corresponding subgroup, there are denominators. And so, but more precisely, in fact, this bijection that I'm talking about between subgroup of non-trivial subgroup of Q and finite adeles induces, when you pass modulo the action of Q star plus, because we want to end up inside a quotient of the adele class space, produce an isomorphism between this set, this quotient set, and the isomorphism points of n hat cross. So if you go modulo isomorphism classes of points, then you reach a set, which is exactly this finite part, XQF. So some visual here. So you start with spec Z, very, very, very easy, very too primitive to include further the number theory that we have behind. And certainly there is a map, theta here, described here, in mapping to the arithmetic site, eventually pointed, because you might want to say, oh, what about the generic point, where the generic point is sent to? So, okay, there is a version of the arithmetic site in which you map the generic point to the adele, which is 0. So then if you take any prime in spec Z, then you map this prime, at least in the easy form, you map to a subgroup of Q, which I denoted HP here, which is the subgroup of Q which has denominator power of P to the N. Okay? And as I said, the generic point is taken in consideration in this statement. So if you start with a point P prime, then you have your adele AP. What is the adele AP? Essentially, it's the adele that has units everywhere except at P, in which obviously you have to catch up in order to have this condition satisfied. So you have to modify it, you have to make in the entry at P the power of P so that you end up inside Z hat. But anyway, this adeles is a class in the quotient extent of the finite Adele modulo Z at cross, because you can eliminate the units in any circumstance. So now one wonder, what we want to achieve. So far are results about the finite part of the Adeles, and we want to include also the Archimedean contribution, because we saw from the start that the Archimedean plays input in the cohomology certain results. So better to enlarge these finite Adele classes by a machine which is geometric in nature. So this usually in geometry, in arithmetic geometry, we do that when we have a scheme defined of, say, over a finite field, and then you take some extension and then you of the scheme of the finite field, and you consider points in the various finite extensions to enrich the scheme. So perhaps you start with a curve that has no point over a finite field, but slowly you get the point, because slowly you enlarge the field Fp, you take finite extension of Fp, and at the end you have a vision of the curve with points when you move to the algebraic closure of the finite field. Here is the similar aspect, but to work with this idea, one has to introduce, together with the topos, the arithmetic topos, we need to introduce a structure sheaf. So this is typical in algebraic geometry. You have spec Z and it's a structure sheaf, and it's only the pair that give fundamental information about the topological space. So which structure sheaf? Well, it certainly should be a structure sheaf with an action of n cross, and we want to reach Z. Okay, so then the intuition is to start with structure sheaf, pre-sheaf, sheaf, because of the topology, which is Zmax. And Zmax is by definition the integers union minus infinity, where the first operation, the addition, is the max, and the second operation is the plus. So by the way, Zmax has inside the very important and unique subgroup of which is infinite and cyclic, which is Zmax star. So there is an action
Sorry, I
of
have a
Zmax.
question. May I have a question?
Yeah.
I have a question. What kind of an algebraic structure is Zmax? Is a semi-ring?
Yeah, Zmax is a semi-field.
Semi-field.
Zmax is a semi-field. Yes, yes. Usually in tropical geometry, people start to work with Rmax because Rmax is a sort of algebraic closure understood in what we say characteristic one in idempotent algebra. But there is Zmax behind the scene, and there is even a smallest one, which are the Boolean. So at the bottom of the story, there are the Boolean. And then unlike the case of finite field, in which you have stepwise finite extension, and eventually you reach the algebraic closure, for in this case, there is nothing. There is a big jump between the first one, which are the Boolean, to the first infinite one, which is Zmax. Okay, so anyway, so we get, there is an action of n cross by endomorphism on Zmax, which is of this type. And this is what we call the Frobenius, the global Frobenius in this context. And the definition of the arithmetic site is just in terms of a pair, the pair of the topos and zero cross with the fixed structure sheaf, which is Zmax. So there is, if you look at the action of n cross in Zmax, there are 2 points in Zmax which are fixed, and these are 0 and minus infinity. So this is the n cross invariant set, obviously, and here is the Boolean. So the Boolean is the smallest semi-field of characteristic one. We say characteristic one in the case of 1 + 1 = 1, or the idempotent occur. So B, these Boolean semi-fields, embeds in Zmax, and the way we like to embed is by sending 0 to minus infinity and 1 to 0. You see the reason. And if you look now at the global section of Zmax in N0 cross, in the topos N0 cross, these are exactly B. And B, in fact, is included, is in its definition here, it's included in the larger subfield, which is Rmax plus. What is Rmax plus in comparison with Rmax? They are essentially two isomorphic semifield. The one is mapped to other by sort of exponential map. So what you saw, what you saw before as a second operation to be plus, in Rmax plus becomes the multiplication. So you don't variate the operation max, but you variate the second operation. So the toposis relations now started to be in terms of pairs, spec Z and O. Now, notice that O is a sheaf of rings here. And here we have the more basic view and sort of below spec Z, if you want, as the arithmetic site being the pair of the N0 crossed hat and this Zmax. So if you, by the way, just a remark, if you pull back Zmax, you don't catch a by theta per star in sheaf theory. You don't catch a sheaf of rings, but in fact you catch a sheaf of sets. And below, much below, at the bottom of everything, there is a very basic fundamental pair, which is the sets, sheaf over a point, with the instruction to choose as a structure sheaf the Boolean semifield. So, okay, so this is said. So now let's try to include the Archimedean place in this story. So far, it's only finite primes, finite adels. A very important property is that unlike what we saw before, so that the action of n cross on Zmax is by endomorphism, when you look at the action of this Rmax on the larger semi-field, which is this Rmax plus, this is an action by automorphism. So in particular, in the extension from Zmax to Rmax, we reach this important property, which makes the story much similar to the case of the Frobenius acting on the algebraic closure of a finite field by automorphism. So this is one role in lifting. The second, well, the theorem, in fact, is that you reach the full double quotient with the Archimedean contribution included adelically as the space of what we would say in geometry, rational Rmax points of A0. Intuitively, what we mean is that we extend the scalars from the semi-field where this finite part was defined to the extension in Rmax. And we were able to identify as a sets these two parts. And moreover, it's not only a simple identification of a set, it's also compatible, as I wrote here, with the action by Frobenius that we have on the left-hand side, and the action, reverse, the action of the Frobenius that we had on the topos side, and the action by R plus max, R star plus, sorry, yeah, that we have on the adelic quotient of the adelic class space. So the action of, by the way, the action of R star plus on the double quotient here is just what remains of the action of the adelic class group when you cut out by this Z hat cross. So if one goes into the proof, then one realizes important points. For example, when you look at the points of A points in this topo extended, there are two kinds of points. The points for which, first of all, a point here is realized, in fact, as a morphism between the point, here is the sets and with the Armax in it included to this pair. And so there are two possibilities, either Armax, so this is said here, either the image here is mapped really inside B within Zmax. And in this case, you get back what you had before. So for the scaling, the finite part of the scaling site. But then there are maps which map the tropical view, say, of the point in terms of subgroups, in terms of totally ordered groups that we saw before, inside the complement. So the image doesn't go straight inside B, but in fact fill up more space. And these are the isomorphism class, corresponds to isomorphism classes of subgroup now of R, of rank 1. It's not that we lose the original idea that we had about identification of points with subgroups, non-trivial subgroup of Q. In this enlarged aspect of the story in which the infinite Adels also enter in, then you catch isomorphism classes of a subgroup of R of rank 1. The earlier one, they were abstractly, but then isomorphic to subgroup of Q, non-trivial. So the difference is that between the interpretation of point in terms of subgroups of Q, in one case, non-trivial, and in this case, when the arithmetic Adele, sorry, when the Archimedean Adele is included as a subgroup of rank 1 in R. So, okay, so here is a sort of explanation, but I think I said enough in the sense that you have at the beginning the finite Adels, the quotient of the finite Adels, and now you add over the Archimedean part of the story, and then you reach by scaling a map to, in fact, a subgroup of R. So what is the scaling map? It maps a pair here, so an element which is a finite Adele and a real number, to the scaling of the associate subgroup of Q, which corresponds to this finite Adele. And this action is invariant. Yeah.
I just want to add one point here, because I think it's quite striking, the fact that when one considers subgroups of the real line, which are of rank 1. So what does it mean that they are of rank 1? It just means that any two elements are commensurable. So a multiple of one is equal to a multiple of the other for suitably chosen multiples. So what is very striking is that when one looks at subgroups of rank 1 subgroups of R, this is a typical example of a non-commutative space. In other words, it is a space like the space of leaves of a foliation. It's extremely simple to define this space, but for instance, it's not possible to inject effectively this space into the real numbers, because the difficulty is that even though you have subsets of the real numbers, you cannot choose in a measurable manner an element of this subgroup for each subgroup. So I think, it's quite important that this is a key point in a way, because it gives probably almost the simplest example of a very significant non-commutative space, which at first sight might look like a simple space, because you say, after all, I'm looking at subgroups of the real line. Okay, I'm sorry to interrupt, but I think it was an important
point. Not at all. If I may, I also add a further comment on your comment, just to connect to the previous part of the story, which is again the quite interesting fact that the Archimedean contribution that I underlined since the start, in place of the fact that we handle spec Z, the Archimedean point is not there. The Archimedean component managed the story in a very sophisticated manner from the very start with the Brouwer group of the real, and here with the implementation of a space which is so enriched, in which we can in fact see CP. So this is the visualization that I told you before. So if you start with any prime non-zero prime number in Z prime element, so then we saw that there is a corresponding subgroup of Q, of non-trivial subgroup of Q, which is denoted here HP, the one for which there are denominators only prime of P. So this is a subgroup, in fact, of Q mod Z. And we also saw an interpretation of this prime, the understanding of this HP in terms of an Adels, a class of finite Adel. So how to build up, how to visualize this orbit, because this was the main point since the very start. I want to have a vision more than the single point P, but I want a circle. I want something which is similar to the knot in S3. Okay, so the idea is exactly at this point in which you take there is a multiplication by elements lambda in R star plus. So you start with HP, which is a fixed subgroup of Q attached to the prime, so to say, and you multiply, you just scale, if you want, this HP by element lambda in R star plus, and then you start to collect quite some number of subgroups of R, which are of rank 1, and they are abstractly isomorphic to HP. So they have to do with HP in the sense they are connected, quote, with HP in terms of a translation, in terms of a scaling, but they fill up a geometry that, in fact, we couldn't see. There is no geometry of that type. And this geometry is really visible in this double quotient. So it's only when you take this non-commutative aspect that you start to understand what is the meaning of the knot attached to the prime. And well, okay, here it's something rather easy, simple. When you take all together, in fact, this was the point of my diagram. When you take all together, you have a really rich collection of orbits inside this scaling site, inside the XQ. But in fact, inside XQ, there are more type of orbits, but those are really the fundamental and in relation to this talk.
Sorry,
yeah.
So my question is related to your comment. So somehow this non-commutative aspect, is it right to think that intuitively now if we deal with something which is non-commutative space, the point has somehow internal structure, and this internal structure gives rise to this this circle, since you are identifying
this is not correct. No, the circle is really inside there as a set of points and as a circle. What you are saying will enter later when one looks at the orbit for the Archimedean place, and it will be just a point divided by a group with 2 elements. But the circle that Katja is dealing with, this circle CP, they are really true circles inside the Adelka space, inside the scaling site.
Yeah. As I said, Adam, there will be other orbits. It's not that I want to neglect the other orbits. I spoke about one of them, the Archimedean orbit, which essentially is the orbit for the action of R star plus that you get when you start with an Adel class that has 0 at infinity. Okay, and so what Alain point out is that together with this fundamental geometric collection of CP, there are other orbits which are all contained in this double quotient. And in there, you see an internal structure, group structure, that in the case of the Archimedean orbit, it's very easy. It's just an action by plus or minus. But still, there is an internal thing to consider in this space, which also it might have to do with the Brouwer group at the Archimedean places. which is in fact Z mod 2Z. So the number theory behind the scene give us this input. Here, what Alain says at Archimedean in the Archimedean orbit, it's the realization in the non-commutative space of this idea that number theory provide to us abstractly in terms of the Brouwer at infinity, or Brouwer var, sorry. Okay, so yeah, you were. So the semi-local analog, why I moved to the semi-local analog? Because after all, we want to get this link. And the link involves only 2 primes, or only 2 knots, in fact, so only 2 primes. So we sort of shrink, in a way, this double quotient of the Adele class space, the scaling site, just to be the minimum possible to consider, to have in it the orbit at P and the orbit at Q. So, but okay, so there is a version, in fact, important version in number theory of this Adele class space quotient already when a finite number of places are included. But notice that the Archimedean place is always there. It's always there from the very start, and its contribution you saw from my very first slides, the fact that in spite of the fact that we consider spec Z, because we handle at the same time Q, there is the Archimedean component which enter in and give us some input at some point. So the definition of the semi-local version of this double quotient, the scaling site, is that you take for S a finite set of places, inclusive, there is always infinity in it, and then perhaps you add furthermore non-Archimedean. And then you have the version, the semi-local version of the Adeles, so which means a product of finite copies of QV and then R at infinity. And then inside there is the integral version, which is denoted here OQS. So those elements that have absolute values, local values less or equal than 1 for every V not in S. Notice not in S. So then there is the group GL1 of this ring. And this is made by plus or minus P to the N1, P to the Nk for any P in S minus infinity, because the infinity is recast here. So, so this is the semi-local version of the scaling site when you take the double quotient by shrinking the collection of primes that you handle in the definition of the original double quotient. And there is an action of R star plus on XQS. This is what remains, again, of the class group action on the full non-commutative double quotient, because after all, you quotient by Z hat ZV star. So that's the reason why you simply see an action by R star plus out of the original action of the class group. So the orbit within XS, first of all, in the very easiest possible case, where S is as small as possible, except perhaps you might say, why not infinity alone? Well, we want to consider the two circle, the 2 knots. So I will start with this semi-local version with S is made by 2 entry, P and infinity. And so the double quotient is very, very sort of modest, but still good enough. So it has a product of QP for the non-Archimedean prime and R for the Archimedean prime. And then you double, you quotient by the action of ZP star and P to the Z, plus or minus P to the Z. So again, this action of R star plus on it. And here are the orbits. Finally, the full collection of orbits in this case. So there is a generic orbit, what we call generic orbit, and this orbit is obtained when you make R star plus acting freely on pairs where the non-Archimedean entry in the Adele element is non-zero, which means it's a unit, and a contribution at infinity, the lambda, the entry in the Adeles, the Archimedean component, is non-zero. So here is kind of a copy of what remains of the del class group inside this. So it's a R star plus that we get as a generic orbit. Notice that the role of generic orbit will be involved in the next part. Then there is the periodic orbit, the one I discussed before, the CP, where at the non-Archimedean entry, you have really zero in the sense of the Adels is as absolute value, the absolute value is less than 1, and lambda is non-zero. So this is, as I said, is the CP that we saw before in a more general context. And then there is the Archimedean orbit. The Archimedean orbit is what I discussed, just telling to Adam before, is when you take pairs where the non-Archimedean entry, so to say, it's in this double quotient, and at infinity you get 0. But then there is still a Z mod 2Z action, because there is still the plus or minus that to take in consideration. So these are the ones that you see, the full collection of orbits in this, for the action of R star, in the case of, very easy case of S equal P infinity. And here is, thanks to the contribution of Alain in this sketch, and here is the way to visualize what we have. We have the orbit CP, and we have a generic orbit that was discussed before, that it's generic. It's like the generic point of Z in itself. So, you know, 0 in spec Z is contained in any open, in the neighborhood of any prime. It's the generic point. Here we have the interpretation in this context, where there is a version of generic orbit, which is, it's dense in CP. And in fact, the quotient topology on this space, in spite of what I said before is a easy space, is quite non-trivial. So the topology is not Hausdorff from the very start. So because of that, you can start with any point in CP in this orbit and have produce a sequence of elements in the generic orbit which has limit in the pair 0y, where y is in CP. So in a way, as Alain said, this CP looks like the limit circle of a foliation associated to a flow. In this case, the flow is R plus. Or if you want the algebraic geometric point of view, this generic orbit behaves like the generic point of spec Z. Okay, so several primes, several orbits. So you might expect, fine, I repeat, I crank the machine now where I include more elements, non-Archimedean primes in S, and there will be an enlarged version of this earlier double quotient when S is P infinity, and there will be several orbits, among which there will be, again, a generic orbit described before, similarly described. In this case, you see each non-Archimedean entry is non-zero, and the Archimedean is non-zero as well. But then there are the periodic orbits, each of which attach to any PJ non-Archimedean containing S. And there is the Archimedean orbits as well, but okay, I just didn't go to that. But the point, again, a nice picture sketch by Alain, is the following: is that the density of the generic orbit in each now of this orbit CP is kind of weird, in the sense that this generic orbit here that you see in green, for density purpose, for density reason, round around systematically over, in a way, each non-Archimedean CP, each orbit attached to a prime, and here there is also the Archimedean point as Archimedean orbit inserted. So it's a vision that starts to be enriched with respect to the earlier diagram sketch, which yeah.
Can I add a comment here? Yes. So I think this is a key place where one can see non-commutative geometry behind the scene. So the best is the following. This picture where you see 3 different primes. Okay, the way to think about it is to see the whirling which was before for a single prime and put three of them parallel, but each converging to the corresponding circle for each of the primes. Okay, so if you put them parallel, what you will have the impression of having three different generic orbit in green. And now the fundamental thing of non-commutative geometry is that you can actually identify the points using matrices. So what you do is using, in this case, 3 by 3 matrices, you can identify the three generic orbits and obtain a single generic orbit. And this is exactly what happens at the level of the description in terms of the C-star algebra. And this is what is written, what Katya is circling around. So in fact, what is quite amusing is that if you can look in internet at people who try to draw spec Z, the spectrum of Z. And in fact, they were getting quite close to this picture, even though they didn't know that the primes, in fact, are associated to circles and not to a single point. But they were, in fact, getting close to drawing a picture of this kind. Okay, so you can continue, Katya. I'm sorry to interrupt.
Thank you. No problem. So finally, I enter in the second part, which is let's try to understand what is the link between these two orbits, or better, in the abelianized, in the cover of the scaling site, which is the maximum abelian cover, which is the Adel class space. So as I said, we want to reach an idea of the image of a pi1 of a knot embedded in the pi1 of the knot of second knot complement in S3. So we need so we have the scaling site here, in which each single orbit attached to a prime is inserted, is naturally geometrically inserted. And then, okay, so there are these two projections. Oops, it doesn't work anymore. There is the Adels, obviously at the top, but then you can mode out and by Q star and reach the Adel class space. So this is what we think of as the maximum abelian cover. I mean, it's not that we think, but it's motivated by class field theory as the maximum abelian cover of the scaling site. And so what we do is take the pre-image of CP of this orbit inside the EQ, first of all. So in this process, you get a saturation of the subset which naturally associated to the orbit, which is the collection of the Adels, in which the Archimedean component is positive and the component at P is 0, and the others do not, I mean, they are units essentially. When you take, because you want to move now from the saturation of the orbit to the Adel space itself and realize the pre-image of CP in there. So when you take the residual action, diagonal action of Q cross on F, on this saturation, because of the prime involved, there is only P involved. This is given simply by the diagonal action of PZ inside Adel. So PZ in Q star acting diagonally in Adel. So then we obtain this description, the isomorphism of the pullback, so to say, the pre-image of CP in the Adel classes, in the Adel class space. So what is it? So P, as I said, is diagonally embedded in this product. So you see by construction itself, this thing is a mapping torus. So a mapping torus for the action of PZ on this compact group. So then the theorem, in fact, that is the main first step in this interpretation, non-commutative interpretation of the link, is that if you start, now remember the node in the most basic visualization. So as Pi1 et al. Of the spec of the finite field Fp, which is by definition the Galois group of the maximal separable extension of Fp, and this is the hat, this is generated by the Frobenius. So if you consider this preimage, which I described before, this is by construction, as I said, the mapping torus of the multiplication by P inside, inside what? Well, you need to think of, you need to have, you need to have in mind this map, which is proper of topology, I mean, et al. Geometry, which is the following. When you have a point P in spec Z, usually in the et al. Topology, we speak of geometric point attached to P. What does it mean? It means that we take systematically the maximal separable extension of the field Fp. And so we realize that, in fact, there is a notion of geometric point, which is, in fact, a map from P itself, so to say, to where spec Z localized at P. So this map is the map which leads the story here, because you see, when this is a map of two, say, schemes, easy schemes, very easy schemes. This is in the et al. Machine. So this is the point P with the et al. Topology, P bar, I mean, with the et al. Topology. And here is a spec of ZP. So spec of ZP is very small. A spec of ZP has in it only 0 and P. There is nothing else. So if you look at the image by UP of this Frobenius inside Pi1 is a functor which is covariant. So if you start from Pi1 of the spectrum of Fp, you end up inside the Pi1 of spec Z localized at P. So if you take sort of the Abelianized point of view of the story, the multiplication by P should be understood inside this et al. Abelianized group, which by class field theory turns out to be exactly the same group, compact group, which enter in the description of the mapping torus. So in spite of the fact that it seems to be unclear what's going on, it's just the realization that the mapping torus, which is constructed out of non-commutative geometry of this scaling site and other class space, has a et al. Geometric interpretation, and in particular, the geometric interpretation is in terms of the maps which govern the mapping torus, so which is this action by P. So the action by P is understood as an image of the action of the Frobenius when you move from the original location of the Frobenius, which is the Pi1 et al. Of the point, inside the Pi1 et al. Of spec Z localized at Z. So,
Katia, can I just, yes, I just want to say one more thing, which is that this fact that the Frobenius is acting by P is exactly the Artin reciprocity in class field theory. So it's quite important to know that. I mean, moreover, what is important also to say is that the Z localized at P, it means that one has inverted all the other primes. And so geometrically, what it means that one is in the complement of all other nodes. Of course, for nodes, this is not
in
possible
analogy,
to say.
Yes. In analogy with the idea of the link, that we end up inside the homotopy of the complement of the second knot.
Yes, but
in
S3. No, but what I want to add one more thing, which is that here, if you want, it is a complement of all other nodes. So, which is only possible for spec Z. Not possible in the case of the sphere, of course, to take the complement of all other nodes, but it is possible for spec Z, because if you want, okay, it means exactly localizing at P. So the correct, I mean, this is the way to think about it. And this is why it will mean that primes are linked to any other prime, because it's possible to take the complement of all other primes at once.
Okay, I need to go further.
Sure,
because otherwise I don't finish. So yes, we will see the case. So here is another sketch of this idea that starting with the circle CP, now we have lifted, we are taking the mapping torus, we are taking the monodromy aspect of the story and reach something over or the holonomy of the periodic orbits, CP. But yes, so this is now what happened when only two primes are involved finally in the description of this link. So we had originally, we saw this slide, so I don't comment anymore in the sense that there is a monodromy obtained by lifting K in the maximal abelian cover. So we are in the maximal abelian cover, in the adelic version of this maximal abelian cover with the Adel class space, and we look at these two primes. So in fact, I say given two primes, P different from Q, inspect Z, then we have now the idea, what is this preimage of the node in the maximal abelian cover? And notice that now we have here the compact group made by ZP cross ZQ cross, because these are the only two primes involved in the story. So the understanding perhaps of this mapping torus and the multiplication by P in what we saw before now becomes perhaps a little bit more intuitive, in the sense that S is now, it's made by three places, PQ and infinity. And okay, here is stuff that I've reviewed before now in this very easy form of two primes. As Alain was saying, here we have the understanding of the local, semi-local Z in terms of inverting at P and at Q systematically. And there is the group action, so I don't go into more into the story. But the important point is written here when you sort of compute what is the pi1 et al. Of the spec of this ring or QS, and say the abelianized form, but it's already abelianized. Here is abelian. So this is in fact the product of the two roots, two units in the ZP and ZQ, ZP star and ZQ star. So yes, so now the time is short, but I think I will. Yes, I think I will say a few comments here, because now for two primes, we have two orbits, CP and CQ, and each of them will have its own lifting called omega P and omega Q in the semi-local Adel class space. And when only two primes are involved, so only two nodes to circle, you see in the story, the mapping torus is the multiplication by P where in ZQ star, because this is only what remains out of the original statement. So this is written in an equivalent form. So pi1, the preimage of CP, it's the mapping torus, so it's written in this form. And this is the mapping torus of the action of P in ZQ star. Before, ZQ star was a product of finitely many ZP star, but in this case, there are only two primes. So you see really the easiest possible version, which is the closest one to the notion of the link, because now the theorem that we have, which is a consequence, in fact, in this very easy setup with two primes, is that the mapping, so there is an action, as I explained before, which is recorded here in the description of the geometric point. And here, ZP, so the Z localized at P, is substituted by some algebra, which has to do with the second not complement. So this is when you localize at Q, not anymore at P. So then the action of P here it's on ZQ star by Frobenius. So the Frobenius implies an action by P on ZQ star. And so this is really the link. Interpret now in both ways as number theoretic and geometrically visualized inside a space which contains the two knots, and in spec Z we didn't have. So I want to finish, because I'm almost over time, with some computation of K-theory of this XQS, not on the abelianized. So just to be really short on this part, but comprehensible, I hope, to understand the K-theory of this localized, semi-localized version of the scaling site, one consider its orbit, as we saw before, and starting with the orbits that we have visible in the abelian cover, which is the Adel class space, the semi-local version of the Adel class space. So if we understand if we start to understand the orbit in the semi-local version of the Adel class space, we will see when two primes are involved, we see several of them. There is a free orbit. There is an orbit attached to the prime P. But there are also orbits which are sort of secondary. It's like when you take a stratification and you have the main stratification of codimension 1 and embedded stratification when more than, in this case, more than one prime is involved. So you will have further orbits when you choose, rather than a single prime, you choose two primes or a primes and infinity, etc. So, so the orbits are all collected here, but the whole point of doing this computation is to understand the K-theory of this scaling site localized when in terms of its orbit. So what I can say is the following. This space, obviously, we know it's a non-commutative space, so it's not of type 1. This is the abelianized space, localized when we take 2 points, two primes. But we have an interesting aspect of this space, which is the fact that the assembly map here is as an isomorphism. Because gamma, the group gamma here is commutative. So we can use the topological interpretation of the story by the K-theory attached to this action, the group of gamma. And in this case, the universal space E gamma is also simple. So in any case, when we pass to the universal space, in fact, we lose the non-commutative interpretation of this semi-local scaling site, and we get an ordinary, in fact, locally compact space. And this is the space we handle with gamma being of this type. So gamma, in fact, gamma, so the cover in a way, it's R2 in this case, and gamma acts on it in terms of action by translation of Z2 and trivially by plus or minus 1. So we lose the non-commutative aspects, as I said, completely. And this space where we enter in with the cover is a nice Hausdorff space of dimension 3. The reason why it's dimension 3 is because there is a R cross R square R2, so this is totally disconnected, so it doesn't implement any further dimension in it. So it's not that we justify the fact that people expected that there is a dimensional 3 sphere, so dimension 3 involved for all possible primes. So the fact that as dimension 3, this space, as I wrote here, is only due to the fact that there are 2 primes involved. So the orbit, the final lamination, with space of leaves of this type, and this lamination descends to Y itself. So again, so now the K-theory of this algebra. So the algebra in question is the non-commutative algebra of groups. So the action by gamma on continuous the group of the Adele space localized at S when S is PQ infinity. When one starts to compute the K-theory, starting with the understanding of the orbits, one find, yes, I want to get to this place. So the space itself for which we want to compute the K-theory has an algebra, a sister algebra, that because the primes are only two, in fact, and there is only the Archimedean prime involved. So we consider only the stratification at the orbit attached to lamination, which is defined by a single contribution, being P or Q or infinity. So we don't, the other contribution are not relevant for the computation, are inessential for the computation of the K-theory. Anyway, the K-theory, the sister algebra here, fit in a short exact sequence of algebras, each of which carry in the information of the orbit at P, the orbit at Q, and the Archimedean orbit. And the Archimedean orbit contributes in the K-theory because you see contribution with very small contribution with the action by plus or minus one, but is there, is essential. So when you fit into the 6 terms K-theory sequence, along exact sequence, then the output, now here very short because I at the end of my time, is that if you look at each single K-theory for K0 and K1 here, then you see easy output like the K-theory, the K0 for R star plus, the generic orbit is 0, the K1 is Z. For P, for the orbit at P, the K0, as expected, is a Z, and K1 as well. Similarly for Q. For the Archimedean orbit, here is the K0 that we get. It's only K0 for the sister algebra of Z mod 2Z. So we there is an implementation of Z2. So when you fit these results in the 6 terms K-theory sequence, first of all, you get that the K0 is Z to the 4, K1 that you see here in Z2. There is still an instance of what, for instance, is the map that connects K0 of B to K1 of the generic orbit. But at the end, with some computation, you have the full conclusion that the K-theory of the algebra attached to this semi-local version of the scaling site has 2 parts. There is a contribution of K0 and K1. K0, it turns out to be Z3, and this in a way reflects the presence of 3 orbits involved, the orbit for P, the orbit for Q, and the Archimedean orbit. And K1, as dimension 2, is Z2, and this is in a way is a reflection in K-theory of the fact that these periodic orbits are dimension 1, each of it. So that is the full story, and I thank you for listening through the end, maybe with but the slides will be available.
Thank you so much, Katia.
Thank you.
That was quite a symphony of beautiful mathematics. So I encourage you now to have questions, how about from collaborators? Alain, do you have any further comments? Masoud?
Sorry? No, not now.
Yeah. Adam?
Yeah, this part was not stated in the abstract. So because I didn't expect to get to this point, but so the idea is the geometric visualization of the link. So we have an idea geometric, what means the link, abstract number connecting two not primes. If we realize the not attached to a prime in a careful manner using non-commutative geometry. This is what we want to, if you want to retain from the talk.
Maybe I ask one question, Katya?
Yeah.
So can we see a quadratic reciprocity also in this context?
Yeah, this is what Alain mentioned before as Artin reciprocity in a more sophisticated form, correct? I mean, this maybe Alain can.
Yes. In fact, I mean, what one can do further, which we are doing with Katya, is to construct a functor which associates to every abelian extension of Q a finite cover now of the scaling site. And then what happens is that the properties which concern, for instance, ramification, concern reciprocity laws, are now totally geometric, and they are visible on these finite covers of the scaling site. And it is an open question because what we get are covers in the sense that they are finite, they have an action of the Galois group, which is transitive on the orbits. The ramification corresponds to the points where the action is not free. And what happens is that the inverse image in this finite cover of the periodic orbits of the circles that we saw before are obtained as disjunct unions, so disconnected unions of finite covers of this circle. And the connected components correspond to the primes which are over the original prime, or if you want, the places of the extension field which are over the place of Q associated to a prime. And moreover, the monodromy of each of the connected components is the action of the Frobenius and corresponds exactly to the Artin reciprocity. So this gives, if you want, a full geometrization of the abelian extensions of Q. And we conjecture with Katya that this extends to the non-abelian extensions of Q, provided one would be able to characterize these finite covers using the structure sheaf of the scaling site. This is an open problem in topos theory, which is, I think, a very important problem, because with Katya, we found that each periodic orbit has a structure of an elliptic curve in characteristic 1, which is a very rich structure. So this
has a Riemann-Roch in it, but the Riemann-Roch real. So this is the part which I haven't included.
Which has real indices, which has real valued indices. So this is a completely new world, which is uncovered if you want, what happens is that the non-commutative geometry gives you the class field theory picture of the extension by Grothendieck Galois theory to schemes.
And of course, with non-abelian extensions, you're not very far from Langlands then.
Of course, because the Langlands program is due to the fact that the dream of Artin, when he did the abelian case, had the idea that the generalization to the non-abelian case would be easy. Of course, this was not the case.
Yes.
And this gave rise to the Langlands program. But what happens is that now we have apparently another access because of these finite covers.
Yes.
And I mean, it's not impossible that, there is a much more geometric access than this other program.
It's a non-abelian, non-commutative, yes.
Yeah, well, okay, of course, you know,
Where
I mean, by
non-commutative geometry
definition,
is
non-commutative
fundamental
geometry.
in this point.
I mean, there is another thing which is rather interesting to say, which is that the key of the three-dimensionality of spec Z that we saw, the key was Brouwer theory. Now, the Brouwer theory, the key finding of the Brouwer theory was done by Brouwer, Haas, and Eminoter. And what they did was to compute in particular the Brouwer group of Q of the rational numbers. And Eminoter at that point was very vocal on saying that non-commutative ring theory should be used in number theory, in the traditional number theory. So I mean, in a way, we are kind of prolonging the dream of Eminoter in some sense. I mean,
Gladly.
Yes, makes sense. Makes a lot of sense. Yeah, great. Yeah.
Okay, great. Anybody else? Omar?
Yes, I have two questions and maybe one comment. So coming back to this non-abelian perspective, if in the classical knots theory, if you want to distinguish knots, the fundamental group of the complement is the simplest.
this is exactly the point, that you have to
Yeah.
pass to the non-abelian situation.
Yes. So is there some way to distinguish these knots corresponding to these primes by something non-abelian? For
Well, in
example,
the traditional étal way, yes, because what you can do is you can look at the étal fundamental group of Z localized at P, and
Yeah,
not
this
at the
is
abelianized.
instance. I'm trying to go back to the statement.
Yeah, but the statement was about the abelian part. So my question is, if you compute the full fundamental étal group, can you say that as knots, these, for instance, C2 and C3 are different, like on a knot and at a trefoil, for instance?
Yeah, so there might be more story, much more story that we haven't seen yet. Yeah, this in my
This will require
technique
to look at the non-abelian covers, yes.
Exactly. So it involves technique that at the moment with the maximal abelian cover, we don't have at hand yet. Geometric technique to be more sophisticated in what you ask. Yeah. To give answer to your question, which requires a more geometric interpretation, precise interpretation of the two knots. So this is, as I said from the start, this is class field theory reflected geometrically in the Adel class space semi-local in solution. But
I cannot
as Adel
resist.
says, oh, what?
From asking next question. Do you have some idea maybe how to extend the theory of knot invariance, like polynomial invariance, like John's polynomial, Alexander polynomial?
Yes, thank you for putting in a very
that
interesting question, open question.
Their arithmetic counterparts. What could be that?
Yes.
In which part of mathematics
I mean, it's
related to arithmetic?
There is so many. Yeah, I understand, because arithmetic topology has more developments than what we simply, in a way, broke the glass, the ice for the first interpretation of the link. But there is a lot of open question, interesting, as you say, that they still need to be interpret in this non-commutative version when we go higher than the maximal abelian cover, hopefully in a topos form.
Yeah, but to be more precise in what he was saying, in fact, Masoud had this idea at some point, and but let me try to say something which is by itself is wrong, but which is suggestive. So what is suggestive is that this whole story at the non-commutative geometric level is full of type 2-1 factors. because the Adel class space, in fact, by itself is type 2 infinity, but what you have is very natural 2-1 factors inside. And when I was talking about these finite covers will give you naturally a subfactor of the type 2-1 factors which are around. So it is not impossible. It's not impossible, but I'm not saying it's possible. I'm saying it's not impossible that at some point later on, okay, one would find indeed a relation between the factors involved and the subfactors involved in the finite covers with, for instance, the von Jones polynomials.
Yes. Yes.
But if you want, at the number theoretic level, people have thought about your question, and it turns out to be related to the Iwasawa theory and such things. But the question now of relating it to type 2-1 factors is much more interesting.
Yeah. There is also this arithmetic Chern-Simon theory that people adapt the real Chern-Simon to these arithmetic situations and get invariance. And that also resonates very well with this project. I mean,
yeah, exactly.
Really,
So I think,
this is the right approach. Yeah.
Yeah, it's clear that there is a lot to be discovered in this story.
Yes.
But in a way, I mean, what makes us very confident with Katya is that, you know, there were lots of speculations done by other people about possible relations. And when we heard about that, we just looked at what we had since ages, and we found that it fits exactly, you know, with all these speculations. So in fact, it's very comforting, including for the approach to the Riemann hypothesis, because it says that the space which is there, which is provided by class field theory, is really the right space to look at. I mean, this is for sure.
It's great.
Yeah. So I have some comment about your categorical perspective in the language of topos theory and all this stuff. So Jones polynomial was invented in the context of the classification of von Neumann algebras. But very quickly, it turned out to be quite clear that it could be categorified under the name of Chovanov homology.
Yeah, my colleague. Yes.
Yeah. So maybe this invariance are so you are starting from this categorified level. So maybe they could be easier to obtain starting from this abstract level. Maybe it's almost there.
Thank you for a comment. I will investigate it with the Kovanov. Yes.
Yeah. And I have one question more. You said about this two-dimensional lamination. It's a foliation of dimension 1. Can we speak in this context about an analog of a Godbion-Weil class or a number?
I don't know. Simple as it is.
No, I can answer this question, yes.
Okay, yes.
Yeah. I mean, of course, we know in non-commutative geometry that the Godbion-Weil invariant in terms of the foliation is obtained by the derivative of the fundamental class. I mean, this is an old paper which I did in 1980, and which, for instance, proved that if the Godbion-Weil invariant is non-zero, then the foliation has to be of type 3. So here it's a different story because the foliation is of type 2, but somehow, if you want, this foliation is in fact coming from a type 3 because the original BC system was of type 3. So one has to consider, if you want, the cross product construction now by the action of R plus star and the corresponding foliation. That will be of type 3, and so there is a chance that this one would have a non-trivial Godbion-Weil. Otherwise, no, because it's type 2. But this is this is almost the beginning of non-commutative geometry. So I mean, it's quite an old story.
Okay, thank you very much.
Okay, anybody else?
Anybody
else?
one question.
Adam.
Yes, I wanted to ask about this field with one element. How this is somehow related to this topic of the so-called dequantization, not quantization, dequantization. And I'm a little bit puzzled by this connection.
But that's another talk. I mean, you know, that's a totally other talk. So, I mean, we could discuss for 1 hour about that. I mean, there is a paper which we wrote with Katja, which I really recommend, which is called The Metaphysics of F1, which is dedicated to Yuri Manin and which you should read because we discuss exactly your question in great, great details in this paper.
Yeah.
Okay, good.
Okay, and maybe one follow-up question. Is it somehow related to the notion of the decoherence, which is one of the central notion in quantum mechanics, and the main concept of decoherence is related to the fact that you have some you are taking the squares of some sums of some ingredients, and the square of the sum is the sum of the square. Somehow this mixed terms are vanishing, and this somehow reminds me those concepts related to this F1 and this Frobenius action, and the fact that this Frobenius is an endomorphism for any n. I don't know.
Adam, you are quite right, but again, this is related to this other paper. It's another discussion. But what you are saying is right. It's true that dequantization is intimately related to decoherence, and it's related to characteristic one. But this is another topic, okay?
And this another paper?
No. You can look in the paper for Manin, but somehow, if you want, there is a whole discussion which cannot be done in a few minutes, and which is related to what you say. But the intuition is correct.
Okay, thank you. I must take a look on those papers. Thank you.
Okay, let me finish by a certain slightly provocative question, if I may. I want to take advantage that I have so many prominent non-commutative geometers present. You see, today I attended another non-commutative geometry talk here at INPAN, and a guy was the speaker, Gabor Sabo, asked a question. So do we have any advantage of the C-star algebraic tools in approaching things like Borel conjecture? And somehow the answer of Gabor was the following. He answered, we C-star algebraists, we do not have any special tools to solve problems in classical topology. And I was not quite happy with this answer. And I was wondering how you guys would answer it, because to me, what always comes to my mind is Kuntz's proof of Bott periodicity using pointed step-lead algebras. I mean, this is a very operator algebraic proof, which I think is very neat, of a theorem, which is, of course, first started in classical topology, where the proof is, I guess, not as neat as a Kuntz's proof. But that's sort of my feeling. What would be your answer to such a question? Imagine that you were a speaker asked such a question.
Well, I mean, it's clear that, for instance, the role of C-star algebras and of cyclic homology and all that was completely obvious in the case of the solution of the Novikov conjecture for hyperbolic groups.
Of course.
So there, I mean, this was a problem in topology, in pure topology. The statement is a purely topological statement, and the proof was obtained by looking at the C-star algebra of the group, looking at what replaces the Durham theory for the C-star algebra of the group, and then just applying the Chern and the isomorphism. So I mean, and this is, if you want, by far, if there is any reason why the Novikov conjecture should be true in general, it's coming from the Durham theory of C-star algebras, which is cyclic homology.
Yeah.
So I mean, of course, people can, can ignore it. They can be ignorant, but I mean, this is a fact, and mathematics is made of facts, not of beliefs, not of opinions.
Yeah, I remember it. I wanted to hear it from you. Yes, I'm very happy.
But let me add one thing, which is that you see in what Katja explained, I mean, at the end, she had the case theory of the C-star algebra. Now you see, if you are without tools of non-commutative geometry, you can think that you are lost when you meet a space which is not Hausdorff, which looks very complicated, and on which you have no understanding. But when you begin to use the sister algebra and compute by hard work, the K-theory and so on, then you see something, and you see something which is real, and you compute, and you might make a mistake and so on. But there, if you want, the role of non-commutative geometry is completely obvious. It is to give you some grasp of a space which normally you cannot grasp because it's too complicated. It's elusive.
Yeah.
When you have this single orbit, generic orbit, which is whirling around several different circles, it looks impossible to understand. And you understand it only by the sister algebra, the K-theory, and such things.
Yeah,
But
yeah.
this is difficult to put in the mind of mathematicians. I mean, this is for sure.
Yes. And I, if I may very briefly add, I think also there is a lot of psychology involved. It gives some inspiration. For instance, everybody knows weak Hilbert-Smith conjecture. This is a very hard problem in topology, okay? And there are many serious topologists working on it, like Edwards, Ranishnikov, Bestina, and they came to a moment at which they had something unpublished, they still had some assumptions, but the moment we realized that we have a very, very general conjecture for compact quantum groups acting on unital sister algebra, which can be phrased in one line, somehow it inspired some people to finish the proofs in topology. So now their assumptions are gone. Of course, we are still far away from weak Hilbert-Smith conjecture. Local triviality is still assumed, but there are no assumptions about your group. I mean, it's arbitrary compact about your group because you have inspiration. All of a sudden, if you can phrase everything in terms of sister algebras, you realize that all assumptions that you made for your spaces are kind of artificial. You don't need them. It's just
exactly. But this is exactly the point. It's exactly the point. It's having the correct point of view. Okay. I mean, and when I say the correct, it's one point of view, but it's one point of view which is, if you want, which has a lot of power. It's just that people have to accept it. I mean, but what is very, very strange is the following: is that you see, okay, when there are new ideas, it's a natural thing that people are resenting them and that they are reacting by saying we don't need it and so on and so forth. Yeah. I mean, but on the other hand, this is a sign of originality. You see, this is the landmark of originality. It's precisely that people, resent it and they say, okay, no, that's originality. Otherwise, you are just doing what many other people could have done. Had done that. So that's
okay, and I think thank you so much. Thank you so much, Katja. Thank you so much, Alain. Thank you so much, everybody. It was a great pleasure to host the community of natural geometers. Yeah, thank you again.
Yeah, thank you, Katja.
Thank you, Piotr, for invitation. Thank you.
So I stop recording.